Hello my dear students. Today we are going to continue our topic about measuring simple harmonic motion. But we are going to solve some problems and answer some questions about this topic or about this section, section 2 in chapter 11, measuring simple harmonic motion. Let's start with some questions. Choose the correct answer. Number 1. In a system in simple harmonic motion, the amplitude depends on. In a system in simple harmonic motion, the amplitude depends on frequency, wavelength, the position of the equilibrium point, or the maximum displacement from the equilibrium point. Let's think for a while. Amplitude. Amplitude, what does it mean? Amplitude in general in simple harmonic motion? Yes, it means the maximum displacement from the equilibrium point. The maximum displacement away from the equilibrium point. So it will be D. What about in an oscillating mass spring system? The distance of the maximum compression of the spring is a measure of amplitude, frequency, period, or equilibrium. What does it mean? The maximum compression in the mass spring system, it refers to, yes, again amplitude, because amplitude means the distance of the maximum compression away from the equilibrium point or the maximum displacement away from the equilibrium point. Both of them are the same. Number 3. So here it will be D and here it will be A, amplitude. Number 3. A total of 5 seconds passes as a child completes one complete swing on a playground swing. You know the playground swing used by children? Yes, the period of the swing is the period 1/5 seconds, 20 seconds, 5 seconds, 1 second. It takes one complete, by the way, the child takes one complete swing during 5 seconds. So here is the period. The period means the time taken to make one complete swing or one complete cycle. So it will be again 5 seconds. The same. Number 4. The frequency of a certain pendulum is 0.5 Hertz. So the period of the pendulum is. How can we calculate the period from the frequency? You remember? F equal 1/T or T equal 1/F. F is the reciprocal of T, inversely related to each other. So to calculate period, you can just make simply 1/F. T equal 1/F. So 1/0.5. 1/0.5 equal 2. If you can calculate it, it will be 2. 1/0.5 equal 2 seconds. Another question. Which of the following factors has the greatest effect on the frequency of a swinging pendulum? Which of the following factors has the greatest effect on the frequency of the swinging pendulum? Friction, amplitude, mass, or length? What do you think? Friction actually has no relation to the frequency. It doesn't affect the frequency. Amplitude also doesn't affect the frequency. It doesn't much affect the frequency. Also, the mass doesn't affect the frequency. But length of the pendulum, yes, the length of the pendulum affects the frequency very much, because the length of the pendulum affects the number of cycles made by the bob of the pendulum. So it will be length, D. Number 6. A certain oscillation mass spring system has a period of 1.2 seconds. Here is T, period. With a 1 kilogram mass, here is M. What will the period be when a 4 kilogram mass is substituted for the 1 kilogram mass? Again, the mass 1 kilogram, if it is substituted with another mass which is 4 kilogram, just substitute 1 kilogram with 4 kilogram, it will be 4 times than the original one. What happens to the period? First of all, we are going to use this formula. T equal 2 pi square root M/K. M was 1 kilogram, then it becomes 4. What happens to the T? It increases, it decreases, and increases how many times, decreases how many times. If m increases 4 times than the original one, 4 under the square root equals, yes, 2. The square root of 4, if it is 4 here, so the square root of 4 equal 2. Then the value of the period will be doubled. So this value of period will be double. 1.2 second, it will be 2.4 second. It will be double of the value. Why? Because 4 under the square root, it becomes 2. Twice the value of 1.2 seconds, so the twice of the value equals 2.4 seconds. Another question. Explain. A student builds 2 pendulums, both 40 centimeter long, have the same length. One has a 500 gram mass, means 0.5 kilogram, and the other has a 1 kilogram mass attached. So this one 500 gram, 0.5 kilogram, and the other one 1 kilogram, different masses, but the same length. Take care. The students start both pendulums swinging, and it's surprised to discover that they have identical periods and frequencies. How could you explain this observation to the student? The student again discovered that both of them have the same, identical means similar, the same periods and frequencies. How? They have different masses, as you see. One of them 500 gram and the other is 1 kilogram. How both of them have the same period and frequency? Simply, as we have studied before in the previous lesson or the previous session, the T or the period doesn't depend on the mass of the pop of the pendulum. It only depends on the length. If you remember, it only depends on the length, since T equal 2 pi square root L over Ag. L. We didn't use mass in the formula. So since the length is the same, so they have the same period, right? So the periods and frequencies of pendulums depend only on the length, as you have said before, not on the mass of the pop. That's why they are identical in both frequencies and periods. Okay? Let's solve some examples or some problems on this section. A child swings with a small amplitude on a playground swing with 2.5 meter long chain. So we have the length here. How can we calculate the period of the child motion and the frequency of the vibration? The period, we are going to use this formula since we have L. So we are going to use this formula, 2 pi square root L over Ag, to find the period. And the frequency, we are going to use this formula, frequency equal 1 over T. So after calculating time, you can easily calculate the frequency. After calculating the period, you can easily calculate the frequency. Let's start with the period. Period equal, by direct substitution, T equal 2 pi square root. Here is a square root. And I open the brackets for L over Ag. L equal 2.5 meter, G equal 9.81. So it equals 31 seconds. Here is a period. Frequency is a reciprocal of period, so frequency equal 1 over T means 1 over 31 equals 0.032 hertz. So we will use these two formulas. Second one is a mass of 0.3 kilogram is attached to a spring and is set into motion with a period of 0.24 seconds. What is the spring constant of the spring? So we need to calculate K. So I'm going to use the other formula for calculating period, T equal 2 pi square root M over K. Why? Because we are asking about the spring constant and we have M. So I'm going to use this one, not this one. This one we use it when we have L, the length. But this one when we use it when we have M or K, and we are going to calculate the other value. So by simple substitution, K, not sample substitution actually, to extract or to get K from under the square root, we are going to make the square root. To get rid of the square root, we have to make it the two sides of the equation squared. Then by cross multiplication, K will be equal to 4 pi power 2 mass multiply T power 2. Again, K equals 4 pi power 2 M over or divided T power 2 by making squared by making the two sides squared to get rid of the square root, and then cross multiplication to get k in alone in a side. So then by simple substitution, by direct substitution, k equal 4 pi power 2 multiply 0.3 the mass divided 0.24 power 2 the period. It equals 205.6 Newton per meter, the measuring unit of k. Another problem. On Halloween, you see an alien that has one antenna made of a glittery foam ball connected to a spring. The spring oscillates with a period of 0.079 seconds and has a spring constant of 63 Newton per meter. Find the mass of the ball. Here we have, again, we need mass, but we have k, so we're going to use this formula, T equal to pi square root m over k. And to get m, again, alone in a side, we have to remove or to get rid of this square root by making the two sides squared, then making a cross multiplication to get m in a side, alone in one side. So m equal t power 2 multiply k divided 4 pi power 2. Again, m mass equal t power 2 k multiplied k divided 4 pi power 2, and again by direct substitution, t equals 0.079 power 2 multiply 63, which refers to k, divided 4 pi power 2. It equals 9.97 multiplied 10 to the power negative 3 kilogram, the mass of the ball. Or we can make it in gram, divided 1000, or we can get rid of this one, 10 multiplied negative 3, 10 power negative 3, so it will be 9.97 gram, the mass of the ball. It will be 9.97 gram, or it's okay, 9.97 multiplied 10 to the power 3 kilogram. Both of them are correct. Another one. A spring of spring constant 30 Newton per meter is attached to different masses, and the system is set in motion. Find the period and the frequency of vibration for masses of the following magnitudes. So, since we are talking about k, spring constant, and we are talking about masses, we are going to use the same formula for period. So, t equal to pi square root m over k. And then the frequency, by the way, find the period and the frequency. So I'm going to use after that f equal 1 over t, this formula for calculating the frequency, but after calculating the time, we're going to calculate the frequency. The first mass, we have different masses, as we said, different masses. The first one is 2.3 kilogram, second one is 15 gram, and the third one is 1.9 kilogram. Here is a solution of the first one. And then you can do the second and third by the same way. Here is t equal 2 pi square root 2.3 is the mass, divided 30, k, equal 1.74 seconds. And by calculating the f equal 1 over t means 1 over 0.74, it equals 0.57 hertz. So we are going to similarly do letter B and C the same way, by direct substitution in these two formulas for calculating the period, then calculating the frequency. Another example. A metal cylinder with a mass of 1.5 kilogram is hung on a spring. When released, the cylinder moves up and down in simple harmonic motion with a period of 1.2 seconds. What is the spring constant of the spring? So here again we have the mass and period and asking about the k. We are going to use the same formula, t equal to pi square root m over k. So k, again it's simple now, it becomes very easy, 4 pi power 2 m over t power 2 by direct substitution. So 4 pi power 2 multiply 1.5 refers to mass, divided 1.2 power 2 refers to the period, equal 10.28 Newton over meter, or Newton per meter, the measuring unit of the spring constant. Another one, a stuntman jumps from a bridge with a bungee cord attached. After bouncing up and down a couple of times, the man settles into a few oscillations of simple harmonic motion. If the man has a mass of 95 kilogram and his period of oscillation is 12 seconds. What is the spring constant of the bungee cord? Again, since we are talking about the mass and period, and you are gonna calculate the spring constant, we are gonna use the same formula, K equal 4 pi power 2 m over T power 2, the same one. You can notice the same one. And again, by direct substitution, 4 pi power 2 multiply 95, the mass, 95 divided 12, which refers to the period, power 2 equal 26 Newton per meter. Another example. A pendulum is suspended from the ceiling nearly to the floor. You observe that the pendulum swings through a complete cycle in a time of 3.75 seconds. What is the height of the room? Here we are asking about height, L, the other formula of period. And by the way, assuming that G or AG equal 9.81, the free fall acceleration, since we have G and L, and we are asking about L and period, so we're gonna use the other formula, T equal 2 pi square root L over G. And to get L, again, in a side alone, we are gonna get rid of this power square root by making the two sides squared, then cross multiplication to get L in a side. L equal T power 2 G over 4 pi power 2. So by direct substitution, L equal 3.75 power 2, the time, the period, multiply 9.81, the G, divided 4 pi power 2, so it equals 2.5 meter. Another one, the last one. Calculate the period of the pendulum that is 1.2 meter long. So here is L, and we are asking about the period. What is the pendulum frequency, assuming that the pendulum is on Earth? Assuming that the pendulum is on Earth means that G equal 9.81. So now we have G and we have L. We are going to use which formula to calculate the period? Yes, the same one. To calculate the period, we are going to use the same one. Then find the simple pendulum frequency. You can do this problem as a practice, homework, do it. And see you next time for section 3. Be ready for section 3 and study well this section. See you.